Swayam Prabha. Digital India. Educated India.
Let us continue our study of set sizes. So in the last lecture we have seen several examples of countable sets. Today we will look at examples of sets that are not countable. Okay. A set which is not countable is called an uncountable set, which is same as not countable. So there do exist uncountable sets. We will see several examples. But first of all, proving countability was somewhat easy. So you propose an injective map from, let's say, A to N, or a surjective map G from N to A. It is injective, surjective. So similar techniques are used to prove A is countable. Okay, but now if I want to prove that A is not countable, what do I have to show? One possibility is you cannot have an injective map from A to N. This is one way of doing it. And there is yet another way. No map in the other direction. You can always construct a map from N to any infinite set which is injective. But any such map can be, no such map can be surjective, okay, or I can say bijective. So we will typically take this approach. We take any arbitrary map, and there are several ways. You may assume that it's a bijection, then arrive at a contradiction. Another option is take any map and prove that it cannot be bijective. Okay. So a technique which is often used for proofs of this type is called a diagonalization argument, or proof. And such proofs date back to Cantor, who was the first to study different types of infinities and raised an important question called the Continuum Hypothesis. I will briefly mention it at the end of today's lecture. So, our first result is that the set of real numbers R is uncountable. So let me now supply a proof based upon diagonalization argument. Okay. So instead of proving this statement, I will prove that this interval 0, 1, which is the set of all x real valued, such that 0 is less than equal to x, this is less than 1, so set of all proper fractions, you may call it, is uncountable. Why does it establish the uncountability of R? If R is countable, then any subset of a countable set is countable. So if this is uncountable, R cannot be countable. Okay. So these are essentially proper fractions. Now note that every such proper fraction can have a decimal representation of the form some decimal digit A2, A3, A4 and so on. So each AI is a decimal digit. Okay. So every proper fraction can be represented like this. That's quite obvious. For example, pi minus 3 is 0.1415926535, so on. And you have, let's say, 3 by 8.375, and this is followed by an arbitrary number of zeros. Okay. And if you have terminating decimal expansion like this, you actually have a second representation of the same number, all nines. This and this evaluate to the same thing. So, if we are dealing with some such numbers with terminating decimal expansion, then we arbitrarily pick some convention. Either I will have this or this. Maybe I will prefer this. Okay. Terminate, then followed by an infinite number of zeros. Whatever, given any such convention of arbitrarily choosing between this and this, we can say that each element in this range less than equal to 0 less than equal to x less than 1 has a unique representation, decimal representation, something like this. Okay. There are cases where there are two representations, but you pick just one, maybe the terminating one. Okay. Okay. But it is important to note that the numbers, fractions that have terminating expansions or that have two expansions should involve either infinitely many zeros at the end or infinitely many nines at the end. Okay. So you keep that thing in mind. Okay. So with this understanding, let me now propose Cantor's proof, diagonalization proof. Okay. So this goes like this. Let f from this interval to n be, you can take any function, or if you want, you may make this function injective. Does not really matter. So we prove that F cannot be surjective. It may be injective, but it cannot be surjective, and therefore it cannot be a bijection. Okay. Which will show that this set has size strictly larger than the size of this set, which is the countable infinity, LF naught. Okay. So, okay, sorry, made a mistake. I made a mistake. It should be just the other way around. Okay, let's have this n to 0, 1. Okay, be any injective function. Okay, and we prove that f cannot be surjective. So that essentially means I have proper fractions of this form: f1, f2, f3, f4, and so on, fn in general, for all positive natural number n. So this is a kind of enumeration process of proper fractions, and the fact that f cannot be surjective essentially implies, this is also an infinite counting process, but the fact that this cannot be surjective implies that this cannot be an exhaustive listing of the elements of the interval 0, 1. Okay. So no matter how you keep on enumerating elements from this, like f1, f2, f3, you are bound to miss at least one element of this set. Okay. So that's the important thing. No matter how we plan to enumerate the elements of zero, 1, we are bound to miss at least one element of 0, 1. Okay. So exhaustive listing, exhaustive counting of the elements of the set is not possible. Okay. So now, with this idea in mind, I propose the first diagonalization proof, but let me start with a picture. Let me go here, it is this picture, okay. So, suppose that f is such a map, okay, from n to the set of real fractions, proper fractions, real valued fractions, okay. So I have enumerated f1, f2, f3, fn like this. So let us say f1 is 0.a11, a12, a13, a14. For each aij is a digit, decimal digit. Likewise, f2 is say something like this. All these are infinite expansions. 3 1, 3 2, 3 3, 3n and so on. Fn is something like this. Now, given this listing, I can compute a proper fraction b as follows. I will force this to be different from 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 this, and so on. In general, the nth decimal digit of b will be forced to differ from the nth digit of f of n. Okay. So how? This is actually quite simple. For example, I can take bn equal to, there are 10 options, right? In decimal digits. So 1, if n equal to 2, 2 if n not equal to 2, or anything, any such thing. Okay. So this is the clean construction. If this is 2, I will take 1 here. If this is anything other than 2, I will take 2 here. Okay. So then, what do I have? This number b differs from f of 1 in this position. It differs from f2 in this position, second position. This differs from f3 in the third decimal position. In general, it differs from f of n in the nth decimal position. Okay. That essentially implies the number b constructed this way. This is also a, you can see, this is also a proper fraction, 0.1 or 2, 1 or 2, 1 or 2, 1 or 2, 1 or 2, and so on. So, also note that bn is non-terminating. Because terminating fractions involve an infinite number of zeros at the end or an infinite number of 9s at the end. But b is composed of digits 1 and 2 only. Right? Therefore, this bn has a unique representation. So, this has a unique decimal representation. Okay, and that is it. Whatever you see here, it is this representation. Moreover, bn is not equal to f1, bn is not equal to f2 because it differs from this, f2 it differs from this, f3 differs from this. Okay, f3 and in general fn for any n. That essentially implies that bn is not in the image of f, or if you want to write it this way, f of n. Not bn, b. B is not in the image of f. So, whatever your function f is, there is at least one integer, one fraction b, which is excluded from the image of f. Okay. So, whatever f you take, you cannot make this function surjective and therefore bijective, even if it is injective. So this proves that the interval 0, 1, closed at 0, open at 1 is uncountable, and therefore the set of real numbers is also uncountable. Okay, so I will talk about what is the relative size of 0, 1 interval and the entire real line. We will see a little later. But let us see, because of this A11, A22, A33, A44, A55, ANN, so this is basically the main diagonal of the two-dimensional matrix. Okay, infinite in both directions, this direction and this direction. And this B is forced to differ with the nth element at the nth position of the diagonal. And that is why this is called a diagonalization proof. Okay. Okay, fine. So, this proves our first uncountability result, that the real numbers are uncountable. So, next, it's a very similar proof. Establishes this. Let sigma be an alphabet. Alphabet is a list of symbols of size greater than or equal to 2, like 0, 1, or it may be the ternary alphabet 0, 1, 2, it may be the your ASCII alphabet or Roman alphabet A, B, C, D up to Z. Okay. Then the set of infinite sequences over this alphabet sigma is uncountable. Exactly, you follow the same diagonalization proof. Okay. So, proof same diagonalization proof works. Okay, in other words, F1 is a sequence. Now forget that 0 point, this thing. Some sequence like this, F2 is a sequence like this, F3 is a sequence like this, Fn is a sequence like this. Then I construct a sequence by forcing this to be different at this position, this to be different from this at this position, this to be different from this at this position, and so on. Okay. So, the same proof exactly shows that set of infinite sequences over sigma is uncountable. But if we look at finite sequences, it becomes countable. I will prove it later. Okay. The implication for this is that if we take any k greater than or equal to 2, maybe an integer, okay, which is the size of this alphabet sigma. So, in the first position, there are k possibilities. Second position, there are k possibilities. Third position, there are k possibilities. And if I consider all positions, that is this, k power alif naught is no longer countable. Okay. So, this is what we have already proved. Okay, so I will come to the exact size of the real numbers little later. Let us see another diagonalization proof. So, this is yet another important theorem. there cannot be a bijection between a set A and its power set. You can write it this way, power set of A, or you can write it as 2 power A, whichever symbol you want to use, it is fine. So, proof, let me first give you a algebraic proof, and then I will show why this is also a diagonalization argument. So, again, f from A to the power set of A, B, an injective function. Okay, injective function. Okay, I will proceed by contradiction. So, let it be a bijective function. That's better. A bijective function. Okay. So, that means 2 power A, the power set of A, is nothing but f of A, small a belonging to the set capital A. Right. So now I construct a subset B of A by collecting those elements of A such that A does not belong to f of A. Okay. F is a function from A to power set. So, f of A is a subset of A. If A is not contained in that subset, I will include A in B. Otherwise, if A is in the subset f of A, capital A, then I will not include it. Okay. Now, let us see how this leads us to a contradiction. Okay. But since we assume that f is bijective, so there exists, so f is bijective, and in particular surjective, so there exists some A in A such that B is f of A. Right. Now let us see what contradiction this leads us to. So now we talk about whether A belongs to FA or not. Suppose that A belongs to f of A. Okay. This implies A belongs to B, because B is equal to f of A. This in turn implies, by the construction of B, I have taken only those A's such that A does not belong to f of A. Okay, so A in f of A implies A is not in f of A. Okay. Conversely, if I assume A is not in f of A, this implies A is not in B, because B is equal to f of A. Just replace this by B, and this implies, by definition of this B, A is not included in B. The reason is that A is in f of A. That is the reason I didn't include A in B. So, I have proved A is in f of a if and only if a is not in f of a. Right? But this is just an absurd conclusion. So this contradiction proves that no function f from a to 2 power a can be bijective. Okay. So this has two implications. You consider this map f from a to 2 power a that takes an element a to a. So this is a singleton set A is clearly injective, which implies the size of A is less than or equal to size of 2 power A. But no f a to 2 power a can be bijective, which implies that this set is strictly larger than this set. Okay. So now, in order to see why I call this a diagonalization proof, let me once again import a picture. Okay. So, but let me introduce a notation. Let B be a subset of A. Okay. So, by the characteristic function of B, denoted C sub B, it's a function from A to the set 0, 1. Okay. A and element A maps to 0 if A does not belong to B, 1 if A belongs to B. Okay. So, you convince yourself that if I am given this function, I can construct B uniquely. Conversely, if I am given B, I can construct this function uniquely. Okay. So, every subset of A is specified uniquely by its characteristic function. Okay, characteristic function like this. Okay. So, now with this understanding, let me show you why the second proof is also a diagonalization argument. Okay. So, come here, here, which picture? This one. Okay. Oops. Okay. So, in this example, I take A equal to n, and let us say that we have enumerated, let's say F1 is the empty set, so it contains no element, so this is 0, 0, 0, 0, 0. Okay. Okay. And maybe f of 2 is just this finite set 2, 4, 6, 8. So 1 does not exist, does not belong to this set, so 0. 2 belongs to this, 1. 0 does not belong, sorry, 3 does not belong to this set, so 0. 4 belongs to this set, so 1, 0, and so on. Likewise, this may be the set of primes at 2, 1, 3, 1, 5, 1, and so on. Likewise, this may be the set of all odd positive integers, 1, 0, 1, 0, 1, 0, and so on. And this may be the set of all Fibonacci numbers, so 1, 2, 3, 5, then 8. Okay. Now I construct this, okay, B, since 1 does not belong to f of 1, I am taking 1 here. But 2 belongs to f of 2, so I am not including 2 in B. 3 belongs to f of 3, therefore I do not include 3 in B. 4 does not belong to f of 4, therefore I include 4 in B, and so on. So, this set will be 1, 4, and something else will come. Okay. So, now this B differs from 1 with respect to inclusion of 1. B differs from f of 2 with respect to inclusion of 2. B differs from f of 3 with respect to inclusion of 3. B differs from f of 4 with respect to inclusion of 4, and so on. Okay. So, B cannot be f of something because it is different at this position, 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 and so on. So, once again you see that this diagonal is coming into picture. Okay. So, this is once again a diagonalization proof. Okay. Anyway, so whatever it is, so the power set of any set is bigger than the set itself. We cannot establish a bijection. So, now, what is the size of R? This is denoted typically as C because it's derived from the word continuum. Okay. Continuum. Okay. So, and we have already established that C is greater than the size of or greater than equal to the size of 0, 1, which is greater than LF naught. Okay. So, we have proved C is greater than LF naught. This is the countable infinity and this is one particular uncountable infinity, that is the size of the real number. Now, I will show that this is, even though this is a tiny part of the entire infinite real line, the size of this is also equal to C. Okay. So, one thing is clear. Okay. So, maybe I will first propose a map F from non-negative real numbers to this X. Take a non-negative real number and map it to X over X plus 1. Okay. It's a very easy exercise that this is a bijection. Okay. Easy exercise. I leave it to you. So, since this is a bijection, I have at least established thus there are as many proper fractions are there, okay, as there are non-negative real numbers. Okay. Now, I still have not seen the entire R, it's only the non-negative part, but that is quite straightforward. Okay. So, first of all, R greater than equal to 0 or greater than equal to, did I use greater than equal to 0? Yeah, greater than equal to 0 is fine. Is anyway a subset of R, and therefore this is less than equal to size of R. Now, if I can propose an injective map from this to this, then the other inequality sign will also hold. So, I consider this map R to R greater than equal to 0. Okay. So, we use a very similar construction. X maps to x over x plus 1 if x is greater than equal to 0. Otherwise, I will again use the same construction, minus x plus 1, but then just shift this by 1 if x is less than 0. So, this maps this entire thing to the interval 0, 1, and this is a similar thing, 0, 1, but once you shift it, it will be 1, 2. Okay. So, G is injective. It is not surjective, but it need not be. This is an injective map. The inclusion map is injective. And in this direction, we also have an injective map, and therefore, R is equal to okay. So, then this unit interval contains as many real numbers as there are in the entire real line, and that number is the continuum C. Okay. Okay. So, that's again interesting. A small bounded interval contains exactly as many numbers as an unbounded infinite set like R. Okay. But anyway, playing with sizes of infinite sets is obviously very tricky. In fact, we in a sense have established that not very formally, but the relation between C and LF naught is 2 power LF naught is C, because again you may concentrate on this interval, and this time instead of considering decimal expansions, consider binary expansions. Okay. So, every proper fraction has some expansion of that form 0, 1, 1, 0, 1, 0, 0, 1, something like that. Okay. And so, there are 2 possibilities here, 2 possibilities here, 2 possibilities here, but you will eventually get all the elements here. So, 2 power LF naught is C. There is only one problem. Again, terminating expansions have something like this. This is same as all ones, right? But this is not a big issue because only some rational numbers have terminating expansions. Only some. whether it is in the binary world or in the decimal world. So, but we know that rational numbers are already countable. Okay. So, you subtract a countable number from an uncountable number, it becomes essentially the same. So, essentially this is the proof that 2 power L if naught is C. Okay. And there exist infinities larger than C. Why? Because, for example, if I consider the power set of R, and the size of that is nothing but 2 power C, and we have already proved that this has to be greater than C. And then if I consider the power set of this, so 2 power C, that is greater than 2 power C, greater than C. So this already gives you an infinite sequence of infinities. Okay. So starting with L if naught, you have C equal to 2 power L if naught, 2 power C, 2 power C. So you see that these are all infinities, but essentially this indicates that there are infinitely many infinities. But this infinitely is actually the countable sets. Because this process is a countable process, right? Start with something, in the next step, in the next step, in the next step, step 1, step 2, step 3, step 4. Okay. So, at least you can see countably many infinities. So, obvious question now is, are there any other infinities? So, it's a big question. In particular, Cantor raised the question, is there an infinity strictly between L if naught, the countable infinity, and C, the size of the continuum, real line. Okay. And okay, maybe I just switch to another slide. So, does there exist an infinite set whose size is strictly between the set of real numbers and the set of natural numbers or rational numbers, whatever you call? So, there is a famous hypothesis which is called the Continuum Hypothesis, which says that no such infinity exists. Okay. Cantor hypothesized this and tried to prove it, but could not prove it, and got mental depression and all that stuff. Later, could not be proved by Cantor. Later, a person called Gödel Kurt Gödel also thought about this continuum hypothesis. He essentially proved that this can neither be proved nor this can, or maybe I put B earlier. Okay, this can be neither proved nor disproved using the axioms of what is called ZF set theory. So, this is Zermelo, Frankel. Okay. And there is another axiom which is called Axiom of Choice, which is actually equivalent to many other axioms like Zorn's lemma, Hausdorff maximum principle, well ordering principle, and there are many things. So, even if you add the extra axiom, the axiom of choice. So this follows from Gödel's incompleteness theorem, and these are all very deep results. So under the Zermelo-Frankel set theory, even if we add axiom of choice or any equivalent form of it, you can neither prove nor disprove the continuum hypothesis. Okay, it's a very stunning result, but Gödel's proof effectively, I would say, says this thing about the continuum hypothesis. There may exist an infinity between Aleph naught and C. There may be no such infinity, and it requires some extra axioms or some other things. Okay, it's not so easy to prove. Anyway, so here you have seen several examples of uncountable infinities, real line intervals, and even bigger infinities than the set of real numbers. Okay, so in the next class we will study why this countability versus uncountability business is important for computer scientists. Okay, so till then, goodbye.